The air inside the control room at CERN was unusually still, as though even the hum of machines had paused to listen. Deep beneath the Swiss-French border, inside a colossal ring of steel and magnets stretching 17 miles long, the Large Hadron Collider had just completed a routine collision sequence. Only this time, it wasn't routine. At first glance, the data seemed like noise. Something wrong with the instruments, maybe. But when the lead physicist leaned in, what he saw on the monitor made his stomach twist into a knot. Something had formed in the collision, a ripple in the fabric of reality itself. A pattern so strange, so profoundly out of place, that for a moment, the scientists in the room just stared. One of them whispered, "That's not possible." They didn't know it yet, but they had possibly created the first synthetic black hole on Earth. Not in a distant galaxy, not in a computer simulation. Here. Now, born in the blink of an eye within the most advanced laboratory humanity has ever built. A tier in space and time itself. And what followed has left physicists and philosophers haunted ever since. Imagine two protons accelerated to nearly the speed of light, colliding with such force that all the known laws of physics are briefly suspended. In that instant, something unexplainable happened. A microscopic region where space-time itself seemed to collapse, folding in on itself. For a fraction of a second, less than a trillionth of a heartbeat, the universe blinked. It matched, almost perfectly, the theoretical signature of a micro-black hole. That alone would have been astonishing. But what came after was beyond anything textbooks had ever imagined. The synthetic black hole didn't behave as it was supposed to. Its evaporation, something predicted by Stephen Hawking decades ago, left behind a trace, a pattern that broke the rules. Particles emerged in ways that simply shouldn't happen, according to any model we know. It was as if reality itself was briefly warped, like the universe let us peek behind the curtain and then slammed it shut. For years, physicists have wondered whether our universe hides unseen dimensions, realms of space that we can't see or touch, but that shape everything around us. The behavior of this black hole didn't just hint at those dimensions. It screamed their existence. And this wasn't some speculative theory tucked away in obscure academic journals. These ideas, large extra dimensions, lowered Planck scales, and micro-black holes, have been the backbone of cutting-edge physics for decades. But theory was one thing. This was data, real, measurable, unignorable. It's one thing to imagine other dimensions. It's another to accidentally touch them. What happened at CERN wasn't fiction. It wasn't a science experiment gone rogue. It was the cold, clinical unfolding of equations that scientists had been solving since the late 20th century. Under very specific conditions, the same ones recreated inside the Large Hadron Collider, space-time could, theoretically, collapse into a black hole smaller than an atom. And now, theory had met reality, and reality didn't respond the way anyone expected. Here's why that matters. Black holes aren't just cosmic monsters swallowing stars in deep space. At the quantum level, they challenge the very core of our understanding. One of the greatest paradoxes in physics is the Hawking information paradox. Does information disappear forever inside a black hole, or is it somehow preserved? Until now, it was just math on a whiteboard. But suddenly, humanity had data. And not just any data. The pattern of decay, the way the synthetic black hole evaporated, suggested something more, a connection to the invisible universe around us, something physicists call the dark sector, the realm of dark matter and dark energy that makes up over 95% of everything, yet remains totally hidden from view. The particles left behind in that instant bore strange anomalies, glitches in the data that shouldn't be there. They didn't match any particle currently in our standard model, the framework we use to explain everything from light to gravity to nuclear fusion. Some believe those particles could be traces of dark matter. Others suspect something more exotic, gravitons, the elusive carriers of gravity, or entirely new particles we've never even imagined. Whatever they weren't from our familiar world. For some scientists, the implications were thrilling. For others, terrifying, because when something this powerful goes off script, the consequences aren't just theoretical, they're existential. For a fleeting moment, the synthetic black hole became the perfect laboratory for testing ideas once thought impossible to prove. Some data hinted at a controversial concept known as ER equals EPR, a theory that black holes and quantum entanglement may actually be one and the same. If that's true, then this wasn't just a black hole. It was a doorway, a bridge, a microscopic tunnel linking different regions of space-time, maybe even different realities. And it didn't last long, just a whisper in the quantum wind, a shimmer of something profound, then gone. But what it left behind, the trail of particles, the unexplained correlations, the anomalies that don't quite fit, those remain, sitting in terabytes of data, waiting for someone to decode them. And as scientists around the world dig through every shred of that moment, some are beginning to wonder, did we just touch something we weren't supposed to? Because buried in the background noise of that experiment was something even stranger, a subtle disturbance in the quantum field, a trembling in the vacuum itself, not destructive, not yet, but like the faint echo of a bell that had just been struck. A warning? A ripple? A cosmic shrug? We don't know. And that's what scares people the most. Because if this was just the beginning, if we've only scratched the surface of what's possible, then the next step might not just challenge physics, it might challenge reality itself. And some have begun to ask, what if we went too far? As news of the discovery slowly leaked from the underground tunnels of CERN to the broader scientific world, the initial disbelief turned into something far more electric, uneasy awe. Because what had unfolded in that dark, sealed chamber wasn't just an experiment. It was a revelation, and it brought with it a heavy question that no one could ignore. If we can create black holes, even microscopic ones, what else are we now capable of? The particles produced in the aftermath didn't behave like good students of quantum theory. Their decay patterns, measured and recorded down to subatomic precision, showed disturbing inconsistencies. They didn't just drift apart. They were connected, entangled, correlated in ways that no known law should allow. These particles were communicating, echoing something deeper, older, more intrinsic to the universe than we've ever understood. When the physicists examined the correlations more closely, some felt the hair rise on their necks. This wasn't random. These patterns hinted at a phenomenon that had, until now, only existed in the most speculative realms of theoretical physics. The idea that black holes are not ends, but portals. Quantum bridges. This is the ER equals EPR conjecture. Einstein-Rosen bridges, wormholes, being physically equivalent to quantum entanglement. If true, then the synthetic black hole didn't just compress mass into a singularity. For a fraction of a second, it may have opened a door between points in spacetime, a tunnel through the quantum foam. And the implications? Terrifying, because we're not just dealing with particles anymore. We're dealing with information, consciousness, the very encoding of reality itself. It would mean that a black hole, even a tiny one, might contain more than mass and energy. It could hold memories, structures, rules. And when it evaporated in that eerie, silent burst of radiation, it may have returned some of that encoded data back into our universe in a form we don't yet understand. What makes this discovery even more unsettling is how closely it brushes against the infamous firewall paradox, a clash between the smooth fabric of Einstein's relativity and the violent unpredictability of quantum information. If a black hole has a boundary where reality itself breaks down, where does information go? Does it burn? Or does it echo back somehow, encoded in the soft hair of the black hole's surface? For decades, these were questions only debated in theoretical papers. Now, Real particles from a real synthetic black hole are on the record, defying every known model and whispering secrets in the language of quantum chaos. And yet, the most disturbing part wasn't the wormholes or the paradoxes, it was the silence, the long, uncertain silence that followed the event. Because while the black hole vanished in a flash of energy, it may have left behind a scar, a pulse in the vacuum. It's difficult to describe what that means. We think of vacuum as empty, but in quantum physics, even emptiness seethes with energy, with the potential to erupt under the right conditions. It's a metastable state, a fragile balance like a ball delicately perched on a hilltop. Stable, yes, but only barely. And the evaporation of that micro-black hole may have pushed too hard. The data showed faint but unmistakable oscillations, ripples in the quantum field that surrounded the collision. To most, it was noise, but to those who understood the deeper implications, it was something far more serious. It was a ringing. Not a gravitational wave in the traditional sense, those would be too small to detect with current instruments, but a kind of microscopic shock wave in the quantum vacuum, a disturbance, as though reality had been stressed and responded with a warning tone. Because here's the truth very few people understand. Our universe may not be as stable as we'd like to think. According to the standard model, the vacuum of space exists in a metastable state, one that, under extreme conditions, could collapse into something else entirely. A deeper, darker valley, a new reality with completely different laws. If pushed over that edge, a bubble of this altered reality could expand outward at the speed of light, erasing everything we know in an instant. CERN's black hole didn't push us off that cliff, but it brought us closer than we've ever been. The energy density reached during its brief existence hovered dangerously close to the theoretical threshold. And this is where science begins to blend with philosophy. Because even if the risk of catastrophe is small, infinitesimal, 1 in a billion, maybe less, it begs the question, should we be doing this at all? This dilemma is known as Pascal's mugging, a thought experiment where a minuscule chance of infinite disaster outweighs any reward, however great. One side argues that scientific discovery is worth any risk. The other, that even the tiniest chance of universal collapse is too high a price to pay. The philosopher Nick Bostrom has warned about this, about the dangers of blindly poking at the deepest mechanisms of reality without fully understanding what we might awaken. And yet, voices like Brian Cox argue the opposite, that nature is more robust than we give her credit for, and the universe can handle our curiosity. Both perspectives hold weight. Both are trying to answer the same question. What are the boundaries of human knowledge? And should there be any? Throughout history, every leap forward, every great scientific upheaval, has been met with fear. Galileo was condemned for daring to suggest the Earth wasn't the center of the universe. Darwin was ridiculed for proposing that humanity evolved from simpler life. And yet, both were right. But this is different. We're no longer just describing the universe. We're changing it. We're creating objects, black holes, that didn't exist before. Objects that bend space-time, that leave echoes in the quantum vacuum, that may connect realms we haven't even begun to understand. It's no longer just physics, it's creation. And every act of creation demands responsibility. As the debate rages on, the team at CERN continues their work. Quietly, meticulously, they pore over petabytes of data, running simulations, recalculating equations, trying to figure out exactly what happened in that 1/1,000,000th of a second. Did they simply witness a quirk of quantum mechanics? Or did they tear a hole in the deepest tapestry of the cosmos? Either way, the universe is no longer the same, and neither are we. By the time the story reached the public, it had already passed through layers of scientific caution and media distortion. Some headlines screamed apocalypse. Others downplayed the findings as a curiosity, a hiccup in a sea of data. But those who understood the language of the universe knew better. This wasn't just a signal, It was a transformation. At CERN, the silence gave way to a controlled urgency. Deep within the data, a new pattern emerged, one that didn't fit any category. The decay products from the micro black hole didn't just include standard particles like quarks, gluons, or photons. They included something else: energy spikes that defied classification, echoes of particles that, to this day, don't have names. No one wanted to say it aloud at first, but it spread like a quiet murmur through the brightest minds in physics. These particles, they might not be from our universe. The term dark sector had floated around for years, used to describe the hidden 95% of our cosmos. Dark matter, dark energy, the things we know exist but cannot see or touch. For decades, the dark sector had remained just that: dark. But suddenly, in the afterglow of a man-made black hole, there was light. Not literal light, but data. Raw, unexplained, impossible to ignore. The signature left behind by the micro black hole didn't justify our standard model. It may have opened a door to the dark sector itself. Some physicists propose that the black hole connected, however briefly, to an entirely separate plane of existence, where different rules applied, where dark matter particles existed not in shadows, but in abundance. What if this wasn't just a black hole? What if it was a key? That possibility lit a fire under a new kind of research. Machine learning systems were unleashed on the data, advanced AIs capable of sifting through quantum signatures at speeds no human could match. These systems weren't looking for conventional particles. They were searching for patterns, non-classical correlations, entanglements that didn't fit any known system. And what they found stunned everyone. Buried within the decay, there were fingerprints, traces of connections between particles that should never have interacted, entangled behaviors that pointed to one haunting possibility. The black hole may have temporarily linked our universe to another, not metaphorically, literally. A flash of connection, a spark of quantum intimacy between realities. These weren't just anomalies, they were intrusions, whispers from outside the curtain of our known cosmos. And yet, even this revelation wasn't the end. Because while physicists worked to understand what they saw, philosophers were left asking what it meant, not for the experiment, but for us. For centuries, science has walked hand in hand with humility. The more we learn, the more we realize how little we know. But this moment, this experiment, marks a turning point. We are no longer passively learning the rules of the universe. We are beginning to rewrite them. To tear a hole in space-time, even briefly, is to challenge the architecture of reality. And to do so without fully understanding what lies beyond is to reach into the abyss, hoping the abyss doesn't reach back. Some warn we've crossed a line, that by creating a synthetic black hole, even for an instant we've pushed the universe too far, that we've invited consequences we can't anticipate. What happens when we learn to control these black holes? To stabilize them? To use them? Could they power civilizations, create portals, store information in ways no current technology can rival? Or could they unravel everything? This is not a distant threat. It is a living question. Because the next run of the Large Hadron Collider is already being planned. Higher energies, more collisions, deeper insights into the invisible mechanics of the cosmos. And the strange, unspoken tension lingers in every meeting room and behind every data set. What if next time the black hole doesn't evaporate? What if we reach the critical point, not just of energy, but of reality itself? The vacuum instability, the theoretical possibility of a chain reaction collapse, remains an open debate. One false move, one uncalculated interaction, could hypothetically ignite a cosmic transformation, a bubble of true vacuum expanding outward at light speed, consuming everything. It sounds like science fiction, but it's not. It's math, it's models. It's part of our current understanding of quantum field theory. So we return to the ultimate question. Just because we can, should we? In the shadow of this discovery, humanity stands at a philosophical and scientific precipice. The synthetic black hole at CERN may have been the most profound creation in the history of science, not because of what it destroyed, but because of what it revealed. We are no longer just students of the cosmos. We are architects, sculptors of space and time, and with that power comes an unprecedented responsibility. Do we keep digging? Do we push further? Do we dare to test the fabric of existence again, knowing full well that reality may not be as robust as we once believed? Some say we are on the edge of a new physics frontier. Others say we're tempting forces we were never meant to understand, that there is a sacredness to the structure of space and time, and that some doors, once opened, cannot be closed. The black hole evaporated, but its echo still resonates in equations, in machines, in minds across the planet. It left behind a question not just for scientists, but for all of us. What kind of species do we want to be? One that gazes into the unknown and turns away, or one that steps through the threshold, unafraid, ready to meet whatever lies on the other side, whatever answer we choose? The universe is watching, and it may already be answering back.